In this session, I'm going to talk about the concept of sets in mathematical perspective and representation of the sets using the Venn diagrams. So, what is a set? Typically, we talk about a set as a collection of objects, right? A set of numbers, a set of items, a set of cards, whatever it is. It's a collection of objects, and each individual object in that collection is typically called as an element. So I can say a collection of, let's say, days of the week. Sunday, Monday, Tuesday could be a set, generally represented with a braces. Now, where do we use sets with respect to probability? Let's assume that I want to perform some kind of an experiment. Let's say I want to throw a dice. Now, when I want to throw a dice, there are different possible outcomes that I can get. I may get a 1, I may get a 2, a 3, a 4, a 5, or a 6. Any of these are possible. So, whenever I am performing some kind of an experiment and I don't know what is going to be the outcome, any one of these are possible. I can't predict what is going to come. Then a collection of all these items, whatever are the possible outcomes that can come, the collection of all these things is what we are calling as sample space. And this sample space is one important concept that would play an important role in probability. That is where the linkage is coming from. Sample space is nothing but the set of all possible outcomes when we are performing any particular experiment. Right? All the possible observations that I can have when I am performing an experiment. So when I'm rolling a dice, these are the various possibilities. So the set of all possible outcomes is 1 to 6. Now coming to a few other terms. Let's say we use a word called event. Event actually is some subset of sample space. That is what we typically call as event. So it will contain one or more elements of the sample space. One or more elements of the sample space, we can have different kinds of events. Probably I'll call a event A as a set of even numbers less than or equal to 6. Or I can say B, another event containing numbers 1, 1 and 4. Or I can say an event C containing a prime numbers less than or equal to 6. So these are all different kinds of events which are primarily the subsets on the total sample space where one or more or zero or more elements of S are present in it. So typically we denote, so if I am saying the sample space as some S and A as some event, when I say A is a subset of S, we denote it like this. Subset is denoted with a C kind of a symbol. A is a subset of S. Especially all the elements of A should be present in S. Then we are calling A as a subset of S. So typically when I know this 1, 2, 3, 4, 5, 6 is the sample space, now even, so A is a set that is containing 2, 4, 6. So because this is 2, 4, 6, it's a subset of S because all the possible values are there in S. Similarly, when I am saying B is 1, 4, B is also a subset of S. But if I say D is 1, 3, 7, then D is not a subset of S because 7 is not present in the sample space. So that's one thing that we need to be comfortable with, the definition of the subset. And if a set, let's say A, does not contain any element, there is no element that is present in A, then we call that kind of a set as a null set. And generally we denote it by the Greek letter phi. Greek letter phi is used to denote the null set. Null set is something, a set which does not have any elements in it. So typically you can look at it like this. Okay. This is a sample space. Think of it like this. So this kind of representation is actually called as Venn diagram. Right? Let's assume this is the sample space overall. Within that sample space, there is an event called A. So let me assume that this is the event called A. Then there is a remaining part. This is the space. This is the part of the sample space which does not belong to event A. Right? So there are some number of elements. If I say these are the elements, they belong to the sample space, but they don't belong to this set A. Right? So those kind of elements which do not belong to the set A but belong to the sample space, that is called as a complement. So A along with A complement generally is denoted either with a small dash on the top or a hash on the top. Either of them. Either I put something like this or I put something like this. So A, the set, the event A, so event is nothing but a subset. So a set A along with its complement should be equal to the total sample space. So if this shaded part is the A, the remaining part of the sample space which does not belong to A is called as A complement. So that's one more terminology with respect to the sets. And generally, if this is A, this entire part is A complement. Right? Then, with respect to the sets, we also talk about a couple of operations that can be performed on the sets. The general operations that we talk of are union and intersection. Union is associated with two or more sets. So typically we call, if I'm talking of two sets A and B, I write A union B like this and A intersection B is written like this. Now what is this union? So we are talking of the elements that are belonging to A either, right? This is more like either. This is a set of elements that belong either to A or to B or to both of them. So I am identifying those elements which belong to A or B or both. Just for an example, if I am talking about A being a set 1, 2, 3, B being a set 3, 4, 5. Then when I say A union B, it consists of elements both belonging to A, B, and A, both of them. So A, these are the ones. B, these are the ones, but B is already 3 is already repeated. So I'm taking the remaining 4 and 5. So this is the A union B. But when I'm talking of A intersection B, it is talking about only the both. Commonalities between A and B. That is what is considered under the A intersection B. So in this case, A intersection B will be only one element 3. Right? Because that is the one that is present in both of them. But if there is no intersection between them, no commonality between A and B, then we call A intersection B as phi, and that is what phi we already have discussed, that it's a null set. Then these two events A and B, these two sets A and B are typically called as mutually exclusive. That's another term that we generally use. Now, if I have to represent them in a Venn diagram form, okay, this is the sample space. Let's say this is A, this is B. Then when we talk about A union B, this entire part is what goes as a part of A union B because it contains A exclusive, B exclusive as well as the combined part. But if I'm looking at A intersection B, I'm only talking about this particular part which belongs to both A and B. And going with this representation, let's say my sample space is both 1, 2, 3, 4, 5, 6. Right? Let's say my sample space is 1, 2, 3, 4, 5, 6. Then how do I represent each one of them? 3 is common. So here is what comes as a part of 3. 1 and 2 are exclusively in A. 3 is there in the middle which belongs to both A and B. 4 and 5 are exclusively in B. Whereas 6 is in the sample space but it is not there as a part of either A or B. So this is the way I can represent the Venn diagram form of all of them together. See, generally, I may have to clearly understand different kinds of things. I should be able to represent them through Venn diagram. Let's take some examples. How do you represent A complement intersection B? Now, what is A complement? Anything that does not belong to A is A complement, right? So this entire outbox as well as this part which does not belong to A, right? This entire B part along with this is A complement. Now out of this I'm only looking at intersection with B, commonality with B, which means only this part. A complement intersection B is only this part, which is as good as I'm looking at, this is what I'm calling as B minus A. Something that belongs to B but does not belong to A. That is what we are calling as B minus A. So typically I can say A complement intersection B is nothing but B minus A. Similarly, another example, A complement intersection B complement. How do you represent it? Okay, A complement, something that does not belong to A. So something that belongs to B part along with this, right? Now B complement, something that does not belong to B. So it could be this along with outside. Now when you are typically talking about the intersection part, only the outside is coming into the commonality of both of them, which is nothing but anything that does not belong to A union B. So I'll call A union B complement. So typically another result is coming out. A union B complement is same as A complement intersection B complement. So like that, the moment you start representing the stuff, you will find different kinds of relationships between different representations of the sets which can help us in solving many numerical problems quite comfortably. right? And even some kind of numericals can very well be worked out with this kind of a concept. All right. So the basic representations of the sets, the basic terminology is something which we need to be comfortable with, which will help us in taking it more further in terms of handling the questions relating to the probability quite comfortably. All right. So thanks a lot for listening to this session. Thank you very much.